My earliest recollection of a scientific discovery was when I was about 4, and it was doing an experiment, and the experiment was my spatial perception. And so it was how to walk from my bedroom to my parents' bedroom without seeing. So I just imagined it and see if I could do it. So I imagined it. I then put a pillowcase over my head and then started walking with absolute certainty of where to go, and went smack into a wall and broke my collarbone. So in terms of experiments, it wasn't very successful, but it taught me a lot in how to actually approach experiments and to perhaps do them a little bit more sensibly. My name is Chris Tate, and I'm a program leader at the LMB. I did my undergraduate degree in Bristol University. That was from 1982 to 85. I then did a PhD in membrane protein biochemistry, also at Bristol. That was with Mike Tanner. I then came to Cambridge and I went to the biochemistry department. So I was there for 3 years working with Peter Henderson, and then moved from one Henderson to another Henderson and worked with Richard Henderson from 1992 here. And I never seem to have left after that. And yeah, here I am. My research is all about GPCRs, G-protein coupled receptors. So these are membrane proteins which are on the outside of the cells, and they bind hormones, neurotransmitters. So these are molecules which transmit messages throughout the cell. So for your body to work, you have to be able to coordinate all the actions inside the body. And so you get release of a hormone, neurotransmitter, it binds to the receptor, and then it gives a intracellular response, which results in the change of the biochemistry inside the cell. And then, of course, you get a physiological response. So think of adrenaline. You know, you're being chased by a lion, you have to run fast, your heart's pounding, you're breathing deeply, and all of those responses are driven through G-protein coupled receptors. So what we're interested in initially was how do these work? How is it that binding of a small molecule on the outside results in changes on the inside of the cell? And the way we've approached that is by doing structures. So we've been doing initially X-ray crystallographic structures, and so making crystals, which was very hard work, and then more recently going on to using cryo-EM. And by using these methods, we've determined how they function, but also how the different ligands have different effects, because they affect the structure of the GPCR in different ways. And this has been very useful in basic understanding, but also in developing new drugs. Because of course what we have is a beautiful description of the molecular details in the orthosteric binding pocket, and you can use that then to design better drugs. I think the choice of the area of research that I have now, membrane proteins, started quite early, because I remember at A-level looking at biological membranes, and the structure we were told was entirely wrong, because the fluid mosaic model for membranes hadn't made it into the textbooks at the time. But it fascinated me about how you had this boundary in the cell, but how do things get across it? How do you actually get signaling? Because you can't have a cell just surrounded like a plastic bag with nothing can go across it. You have to be able to have nutrients going across, but also any toxins going out. So there has to be a permeability, but how do you get the specificity of that permeability? And then in receptors, also, how do you get that binding of something on the outside and a dynamic change to lead to signaling on the inside? So it was a very early on. And then when I was at Bristol in my undergraduate, we had the final year project was something that we spent 10 weeks on, and there's about 3 days a week in the lab. And I chose a topic with Mike Tanner, who was actually ended up as my PhD supervisor. And it was to work on a protein called the calcium magnesium ATPase from red blood cells. Nobody in the lab was working on it, but Mike thought it would be a terribly good idea to have me purify it so we could do the cloning of it. And so basically he just gave me a paper and said, do this. And I had so much fun. I mean, nobody was doing anything like this, so I could just I was just ran loose in the lab, and it was wonderful. And I think to everybody's shock, I got it to work in a few weeks, and they thought, oh, now what do we do? It was just great. And that really cemented my, my fascination with membrane proteins, and I've only ever worked on membrane proteins ever since. The excitement you get in this area is ongoing. There are always peaks of amazing excitement. I remember the first time we looked at the projection structure of EMRE. So this was a multi-drug transporter we were working on. So this was around about, end of the 1990s. And at that stage, we were making 2D crystals and using electron crystallography to determine the structure. And at the time, it was thought that EMRE was supposed to be a trimer. So four transmembrane helices in a trimer, so 12 helices, with a threefold axis relating all of them. That was the idea. And I looked at the projection structure of just determined, and it was asymmetric, and there was not enough density for 12 helices. There's only enough for 8. And you just go, wow, it's just incredible. And then you have to think, well, now what's the structure? How does this actually come about? Because having an asymmetric dimer for a homodimer is, again, not possible. And actually, after a lot of research, it was a completely novel topology in the membrane, with one on the NC terminus on the outside and the other and the NC terminus on the inside. So it's an anti-parallel dimer, which hadn't been seen before. And so it's those things which you don't expect. That's the real excitement of science. I remember when we started the protein engineering on making thermostable receptors, and that started in March 2005. And we thought, I knew it was going to work, but I never realized how well it was going to work. So after a year, it went so fast. And then you ended up with something which was just incredible. And then that was a foundation for the company we set up a little bit later in Heptares. And then every time you get a structure, each structure is new. So the latest structure that we got was the one of ST2 from Vaitish Valajahan in the lab. And it was just so exciting. There were so many novel things about it. It was the fact it was a dimer. There was the fact that the ligand, how it bound, was unique, and how it activated the receptor was unique. How you actually saw those conformational changes going from the ligand to the inside was different. So everything you do when you get a result like that is exciting. And that's what keeps you going. Because I can tell you the troughs in between can be quite deep and long sometimes, but you get over it. There was two, I think, results from our lab which have had a big impact, both in terms of other people around the world and also in our own research. So the first was, as I mentioned earlier, the conformational thermostabilization receptors by systematic mutagenesis. And this really transformed how we could do crystallography on GPCRs. So previously, it was really difficult to get crystals of GPCRs because they're very unstable, and the detergents you would use to get crystals would be quite small and denaturing. And so what we did is make them much more stable in a particular conformation. And this then allowed us to get crystals of the beta-1 adrenergic receptor. And this was a project which Gebhard Schertler initiated in about 1989 when he joined the LMB. And we were still working on it in 2005. And so he had no crystals. Tony Warren had worked for 7 years, no crystals whatsoever. We got the thermostable receptor. It expressed beautifully. He purified it beautifully. And within a couple of months, we had crystals. It was that transformational. And we then got the structure eventually, and it was lovely. We applied that to other receptors. It worked just as well. And on the basis of that was when we founded the company Heptares Therapeutics. That was in 2007, and that was based upon that discovery. And the other tool that we developed was the mini G proteins. And this came from an idea from Byron Carpenter, who was in the lab at the time and had been working very hard to try and make active state structures of GPCRs using G proteins. So the G protein, it just basically, the GPCR opens up and the G protein C terminus just pops into a cleft inside. So we were using just this part of the G protein to try and be able to get these complexes stabilize the active state of the receptor. It didn't work at all. 2 years of hard graft for nothing. And then the idea was then to take the G protein structure from Brian Kabilka's lab and say, okay, well, we don't need 90 kilodaltons of protein. Let's chop away all the bits we don't need and end up with something that was about 30 kilodaltons. And that worked beautifully, and it's turned out to be very, very useful for a lot of people doing other research around the world. So they're the two things which have really made a big impact, both to our research and to other people's research. I think most of our experiments are very, very directed towards trying to get a structure. And I think, there were two experiences which I had which really made a big difference, even though most of it never got published. And that was working on the serotonin transporter. And the serotonin transporter was the project I initially started in 1992 and to try and get a structure. And I was basically about 20 years too early. It was actually solved eventually by another group. And the problem was that it was a horrible, horrible protein. It was very unstable. It required cholesterol for activity. It required N-glycosylation for proper folding. It was expressed at very low levels. But what it taught me was a lot about membrane protein overexpression. Everything that we did afterwards with GPCRs has been based on that. But also, it was really the foundation for thermostabilization, because this was my main project and it was a horrible protein. I couldn't take it forward. EMRE was my side project, and that was an incredibly stable protein. And so it planted the seed in my mind of what would happen if I could make the serotonin transporter much, much more stable, just like EMRE. And it would make life so much easier. You would be able to get a structure. And in the end, that was exactly the strategy which was used by another group. I mean, we made thermostable mutants of the serotonin transporter. It worked really well. But our crystals only ever diffracted to 7 angstroms. And we needed an antibody, which we didn't have, to be able to get the full structure. So that was something which, it was hard, to get scooped like that after 20 odd years of work is not nice. But everything that we learned from that has been used for the GPCR work. The LMB is just an amazing building to work in. Even the old building was amazing to work in, even though it's not so palatial as the new building. It's the people here which make the difference. And when I mean the people, it's not just the scientists. It's everybody who's here. All the support scientists, all the people who work in estates, everybody, the cleaners. When I have guests coming to the LMB, they're astounded by both the quality of the building, but also how beautifully clean it still is after nearly 9 years. But of course, the people, it's the time that they give you. You can have the craziest idea in science, and you can always find somebody to discuss it with. And people really give you the time. And the way the LMB has been set up is so that you can do these crazy ideas, that there's no impediment to doing good science. Whereas, you go to a university and everything just takes that little bit more effort to be able to get the experiments done. You might not have the right bit of equipment, and somebody else does, but then suddenly they're not going to let you use it because that actually came off a grant, or you might have to pay, or you can't use detergent on it, because everything we do with the detergents, and people don't like detergents. And just little things like that, everything is just that little bit more difficult. And of course, the funding here is also magnificent. It's to be able to have the consumable money, to be able to to do what you want is also incredible. So it's all these things coming together makes it a wonderful place to work. I mean, the old building was special in its own way. You know, we were packed in there like sardines. So you really met people, and you mixed a lot with the divisions because there were no, or very few boundaries between divisions. So I spent a lot of time in a rather grubby tissue culture lab with all the people from P&AC, mixed with them, and met some amazing people who, you know, sitting in your own office, you wouldn't meet. So that mixing is so important, the sharing of ideas. And I remember once I was up in the canteen in the old building, and I was just sitting there, and one of the PhD students from David Neuhaus's group came along. And we were chatting about his research. And he suddenly mentioned, and then I just ligated this peptide onto the end of my protein. And then I suddenly went, what? How do you do that? Because that was exactly what I was looking for to help with the project. And that ended up being one of our major publications of getting a structure of the arrestin bound to the beta-adrenergic receptor. And so it's these chance conversations are amazing. And I have lovely memories of talking with Max Prutz up in the canteen, and he was just so lovely to talk to, and he just wanted to know about your science. You know, he didn't want to talk about himself or his science, he just wanted to talk about your science. And these things, that's what makes the LMB so special, really does. How do you become a good scientist? That's a tricky one. You've got to be absolutely driven, pedantic about your science. But then you mustn't be driven so much that you don't listen to other people and try other things. You've got to be open to new ideas, but then you've got to be determined to make this idea work. So it's a strange mixture of things. I mean, dedication, definitely. You just have to, it's putting the time in, but also thinking. You've got to work hard, but you've also got to think hard. And then you've also got to play hard, because, you know, just being stuck in the lab 24/7 is also not enough. It's all the best thoughts I have ever had have not been in the lab. Because when you're in the lab, you're thinking, you're working, you're focusing on what's in front of you. But if you want to think sideways, you have to get out of the lab and do other things. So whether it's sailing or walking or cycling, it's just relaxing your mind, doing Tai Chi. Anything that relaxes your mind and then allows it to think laterally. And so important. Oh, I have lots of favourite things to do away from science. I've been doing Tai Chi for the last 23 years. I'm a Tai Chi instructor, which helps me to relax and to meet other people outside science, which is lovely. I used to be a sailing instructor. I did a lot of sailing, did cruising on the Broads, sailed over the North Sea, over to Holland. Did a lot of cycling, cycle touring, cycled from Land's End to Donegroats, love hill walking in the mountains in Switzerland, done the Walker's Haute Route from Chamonix to Zermatt, and Tour de Mont Blanc, fantastic. Being outside, what more could you want? Throughout my career, I've had lots of people who have influenced me and helped me along my way as a scientist. And I think I've already mentioned the first person who was my chemistry teacher, Roger Barnes. And he was an amazing scientist. He got a PhD from Bristol, and he was working on doing a biochemistry course for Nuffield A-level science. And so we were the guinea pigs. We actually did a lot of the experiments, like making phenol oxidase from potatoes. And it was that love of being in the lab which I really, really enjoyed. And then in my first real lab experience of then going on to, in the undergraduate, being in the lab, then Mike Tanner, both an undergraduate and then at the PhD, he taught me how to make hard decisions. Because I remember halfway through my PhD, it was a PhD project of trying to isolate a cDNA clone for the calcium magnesium ATPase using lambda GT11 expression cloning, which was the only method which has never ever given rise to a cDNA clone using an antibody for membrane proteins. So the method was at fault, not me. But you don't see that at the time. And then about halfway through my PhD, Mike came to me one morning and says, Chris, I really think you ought to change project. This is not going to work. And, the instantaneous feeling is just anger. I've worked really hard for a year and a half, and now you're telling me to change. And, I sat and thought about it for a few days, and I thought at the end of the day, well, who knows more about science? Me as a PhD student? Him as my supervisor. So I went and had a chat, changed project, and ended up with 4 papers, 3 first author papers from it in the last year and a half. So, taking advice is important. Making difficult decisions is really, really important. And knowing when to terminate a bad project is critical in that. And then later on, I then moved to biochemistry in Cambridge, and there Peter Henderson, he taught me really the importance of being pedantic, of really the discipline of numbers in terms of radioligand binding assays, or these are transport assays as well. And all the radioactive work that we've done has been based on that, and it's just wonderful. It really gives you good insights into your activity of the proteins. And then I suppose my biggest influence, of course, has been Richard since I've been at the LMB, Richard Henderson, that is. And he's an amazing guy. I mean, he's so enthusiastic, always got some advice, always open for a chat and to discuss science. Although you do have to be very careful. So, if you come along for a 10 or 15 minute chat, you normally have to allow about 2 hours because we always get diverted and talk about other things. But he's also been very, very kind in giving me difficult advice as well. Like on my interview, or as he called it, little chat when I came here, which I think lasted most of the afternoon and evening. He said, Chris, if you come to work here, you won't have anybody else working for you because ruining one person's career is enough. Which I thought, okay, if that's how it is, that's how it is. And then later on, in the number of years down the line, when I still hadn't got a structure, he did pointedly tell me that, I could only show promise for a certain window of time, and then you have to produce. So I took that as the writing on the wall, and I have to do something. So, advice doesn't have to be nice, but it can be timely. So Richard has always given very good advice. So that's been very helpful. When you start your scientific career, it's a dive into the unknown. You don't know where you're going to end up. I know some people might have very decided goal of, I'm going to become, a Max Planck director or something like this, and this is where I'm going to end up. But really, I just enjoy what I'm doing at the moment. I've always lived far more in the moment and thought, this is what I want to do. This is just amazing. Being at the bench doing scientific research is amazing. And that has always been my focus. I've never had that focus of, I want to be at a certain position in my career. Yes, you think, it'd be nice to carry on, do a postdoc and maybe go on from there. But I've never really had a driving ambition to go to a particular point. Life is far more fun. Let's see where it ends up.